Hello friends, my name is Tushar and today I'm going to talk about how to find maximum flow using Fulkerson method Edmonds Karp's algorithm. Here we have a directed graph with source S and sink T. There are nodes in between. Every edge has certain capacity. Edge S1 has capacity 2, so we can move 2 units of item from S to 1, and edge 2-3 has capacity 1, so we can move 1 unit of item from 2 to 3. Given such a graph, you have to find out how many maximum units of item you can move from S to T, and that is called maximum flow for this network. So you can imagine many applications for such kind of network. This could very well be a pipeline network and you would want to find out how much oil you can move from S to T, or this could be an internet network and you would want to find out how many IP packets you can move from S to T. So Fulkerson suggested a method to find out the maximum flow. Let's look at that method. Let's talk about flow. Flow is the actual units of item moving on an edge, while capacity is the total capacity of that edge. So right now, since no items are moving through any edge, the flow of every edge will be 0. So this is the capacity while this is the flow. So residual capacity is the total capacity minus the flow. Basically, what is the spare capacity on that edge? So the residual capacity right now on this edge is 2 minus 0, 2. Here it is 3 minus 0, 3. Here it is 3 minus 0, 3. 1, 3 and 1. So an augmented path is a path from S to T such that the residual capacity on every edge of that path is greater than 0. So let's find one such path. So S to 1 and 1 to T. S to 1 and 1 to T. So here the residual capacity is 2, while here the residual capacity is 3. So the minimum of the two residual capacity is 2. So basically saying on this path, at max we can move 2 quantity of item. So the flow on this path now is 2. So let's increment this flow. So this becomes 2 and this becomes 2. So the residual capacity here now becomes 0 and residual capacity here now becomes 1. Also you can notice that the flow will never exceed the capacity. You cannot flow more item through an edge than the total capacity of that edge. Let's find another augmented path from S to T. So we can go to S to 2, 2 to 3 and 3 to 1. So S to 2, 2 to 3 and 3 to T. So the residual capacity here is 3, here it is 1 and here it is 3. So again the bottleneck here is this edge 2, 3. So the maximum capacity this path can handle is 1, which is this 1. So now the flow through this path is 1. So this becomes 1, 3, and the residual capacity here is 2. This becomes 1, 1, and then the residual capacity is 0. This becomes 1, 3, and the residual capacity here is 2. There is one more path possible from S to T, which goes from S to 2, 2 to 1, and 1 to T. So S to 2, 2 to 1 and 1 to T. Here the residual capacity is 2, here the residual capacity is 1 and here the residual capacity is also 1. So giving us a flow of 1 through this path. So since one more item is flowing through this path, this now becomes 2. So the residual capacity here is 1. This now becomes 1. So the residual capacity here is 0 and this becomes 3. So the residual capacity here is also 0. Now you cannot find any more augmented path. So the maximum flow in this network here is 4. So this algorithm is Fulkerson algorithm. What Edmonds Karp suggested was to find this augmented path, use a BFS search, and this helped in greatly reducing the time complexity for this algorithm. Let's discuss one more thing before looking at a harder example. Let's say we have 2 nodes with a capacity of 7 from 1 to 2 and capacity of 3 from 2 to 1. So, and let's assume that these 2 nodes were part of some flow network. let's say there's a flow of 5 from 1 to 2. So here the residual capacity will be 2. What that means is the residual capacity from 2 to 1 will increase by 5. So the total residual capacity here will now become 8. From 2 to 1 will become 8. Why? Because we can stop moving those 5 items from 1 to 2. So that gives us capacity 5. Plus 2 to 1 already has a capacity of 3, giving it a total residual capacity of 8. So what that means for this graph here is, since there is 2 flowing in this direction, if needed we can flow 2 in back direction. So there is a residual capacity of 2 on this path from 2 to S, a residual capacity of 1, a residual capacity of 1, a residual capacity of 1, a residual capacity of 3, and a residual capacity of 2. Since all the current capacity in the reverse direction was 0, we just added the whatever flow was to the residual capacity in the reverse direction. So using all this information, let's try another example. So let's apply the algorithm on this residual graph here, where the source is A, sink is G. So basically we are looking for the maximum flow from A to G. The residual capacity on every edge right now is same as total capacity because the flow is 0. If there is no edge from one node to another node, then the residual capacity on that edge will be 0. So for example here there is no edge from G to F, so the residual capacity in that direction is 0. Also we have this Q parent map and visited set for doing BFS. So starting from A, let's find an augmented path to G using BFS. So first thing we do is we add A to our Q and to visited set, saying that A is visited. Now looking at A, let's find all the neighbors of A and see which one who has residual capacity greater than 0. So here A has 3 neighbors, B, D and C. C is also considered a neighbor of A because there is a arc in this direction, although the capacity on that is 0. So we are looking for neighbors who are not visited and whose residual capacity is greater than 0. So B and D are 2 such neighbors whose residual capacity is greater than 0 and who are not visited. So what we're going to do is, we're going to take A out, make it current, then we're going to add B and D into this queue, mark B and D as visited, and also say that update this map saying that B got introduced by A and D also got introduced by A. Then we are done exploring A. Then we are going to go to the queue. So we are going to go to this queue until the queue is not empty. So we go to the top of the queue, remove top of the queue, and then current becomes B. So now from B we are exploring neighbors who have residual capacity greater than 0 and who are also not visited. So this arc here has a residual capacity 0, so this is not useful. This here C has a residual capacity 4 and C is also not visited. So let's add C to the queue, C to the visited set, and also say that C got introduced by current, which is B. Then another, this E also cannot be visited because the residual capacity on this arc is 0. So we are done exploring B. So let's again go to the queue, get the item at the top of the queue, which is D, and mark current as D. So we are at D. So now we are exploring neighbors of D. So this A, the residual capacity on path to A is 0, so A cannot be used. Residual capacity on path to C is 0, so C cannot be used. Residual capacity on a path to E is 2, so E can be used. And E is also not visited. So we put E into the queue, E into the visited set, and say that E got introduced by D. So E got introduced by D and the capacity here is greater than 2. Then another neighbor of D which has residual capacity greater than 2 is greater than 0 is F, which is 6. So we are going to explore F2. So we are going to add F to the queue, say that F got introduced by D, and add F to visited set. Okay, so we are done exploring all the neighbors of D, and we have yet not reached sink. So let's again go to the top of the queue and pop the next element out. So the next element out is C. So we are at C. So there's a residual capacity of 3 on this path from C to A, but A is already visited, so we cannot visit A. There is a 0 residual capacity here, so this is not useful. There is a residual capacity of 1 from C to D, but D is already visited, so we cannot visit D. There is a residual capacity of 2 from C to E, but E is also visited, so E cannot be visited again. So we are done exploring C, and C cannot explore any more neighbors. So let's again pop from the top of the queue. So next element is E, which is this. So as soon as E gets explored, E has a neighbor 1 and G is that sink. So what happened was we found sink, which is our destination. So what we're going to do is we're going to terminate our BFS. Since we found our destination, add the fact that G got introduced by E, and now we are going to trace the path how we reached G. So to trace that path, we go to this parent map. So G got introduced by E. So I have my G here. G got introduced by E, so I'm going to put E here. E got introduced by D, so I'm going to put D here. And D got introduced by A. So now, once we have reconstructed this path, let's see what is the minimum residual capacity on every edge. So A to D is 3, D to E is 2, and E to G is 1. So the minimum capacity on this path is 1. Residual capacity on this path is 1. So the maximum flow we can get in this path will be 1. So what we do here is, the flow we can get in this path is 1. So what we do here is, once we get that flow, we are going to add it to the flow we have found till now. So 1 plus something, the future flows to come. And then we're going to subtract this flow from every residual capacity on this path. So we go to E to G, and since this value is 1, this becomes 1 minus 1, so this becomes 0. And we are going to go into the opposite direction and increment this guy's residual capacity by 1. So this really becomes 1. Then I'm going to go to D to E. So D to E, reduce this guy's residual capacity by 1. So this becomes 1. And increment this guy's residual capacity by 1. So this also becomes 1. And then I'm going to go to A to D. So A to D, decrease this residual capacity by 1. So this becomes 2. 3 minus 1, 2. And increase this residual capacity by 1. So this becomes 1. So this is our one iteration and one augment. This is how we found one augmented path from A to G. So let's continue looking for more augmented path from source to sink similarly. So I have cleared up all my queue, map and visited set for starting a new BFS. So let's find another augmented path from A to G in this updated residual graph. So A has neighbors B and D, so current becomes A. A is visited, and it has neighbors B and D whose capacity is greater than 0. Residual capacity is greater than 0. So we'll say that B is coming from A and D is also coming from A. Now we go and find the top of this queue, and that is B, and remove it from here and look for the neighbors of B whose residual capacity is greater than 0. So that's C, and that's it, and here is 0. So C, so we add B and D to visited, and then we add C here and say that C got introduced by B, and B has no more neighbors to be explored. So we again go to the top, get the top of the queue. So this time current becomes D. This time current becomes D. look for the neighbors of D which is not visited and has residual capacity greater than 0. So that's E and F. So let's add E and F to our visited set. Say that E and F got introduced by D, and also say that E and F, also add E and F into the queue. So next let's again pop from the top of the queue. So my current becomes C. C has no neighbors which is not visited and has residual capacity greater than 0. A is visited, B has no residual capacity, E is already visited, and D is already visited. So we cannot do anything about C. So let's get E out. So current becomes E. E has, so last time this guy was 1, so we moved from E to G, but this time this value is 0, and B is already visited, and otherwise, and D is already visited. This is 1, but D is already visited, so E this time has no more neighbors to be explored. So next we again go to here and try to get the top of the queue, so this value is F, and try to explore neighbors of F. So F has this D, but the residual capacity here is 0, and G, the residual capacity here is 9. So again we found our destination, which is sink. So after we found sink, let's retrace the path back how we reached A. So first I'm going to note that G got introduced by F, which is current. So let's retrace our path back to A. So G got introduced by F, and F got introduced by D, and D got introduced by A. So let's add the residual capacity and put the residual. So A to D residual capacity is 2, D to F residual capacity is 6, and F to G residual capacity is 9. So the minimums of this residual capacity, which is 2, will be the flow for this path. So the flow for this path will be 2, and we'll add this flow to the maximum flow. So till now we have found 1 plus 2, 3 maximum flow. Also what we're going to do is we're going to go in here and subtract this flow from in this direction and add in the opposite direction. So 9 now becomes 9 minus 2, 7. So the residual capacity in this direction really becomes now 7, and the residual capacity in the opposite direction now becomes 2. Residual capacity from D to F now becomes 4, 6 minus 2, 4, and residual capacity in the opposite direction becomes 2. And finally, residual capacity from A to D becomes 0, and the residual capacity in the opposite direction becomes 1 plus 2, 3. So we found one more augmented path, and we added to the max flow. There is one more augmented path to be found, and let's find that next. Sorry, I misspoke. There are 2 more augmented paths to be found. So again, starting from A. So A goes into the queue and visited set. So we'll take A out of the queue and explore neighbors of A which has residual capacity greater than 0 and are not visited. So B and D, but the capacity here is 0, so only B can be explored. So let's add B to the visited set and say that B got introduced by A, and add B to the queue. Now A has no more neighbors, so we take again from the top of the queue, so that will be B, and explore neighbors of B. So neighbors of B is A, but A is already visited. This is C, the residual capacity is greater than 0, so C goes here, C got introduced by B, and C goes into the queue. And E here, residual capacity is also 0, so we cannot do anything about it. So that's about B. Let's move on to next one at the top of the queue, which is C. So C has 2 neighbors, D and E, where residual capacity is greater than 0, 1 and 2. So we say that D got introduced by C and E got introduced by C. Add D and E here and D and E here. So next, again, let's get from the top of the queue. So this time it becomes D. So D has E, which is where residual capacity is greater than 0, but E is already visited, so we cannot visit that. So we'll visit F. So F got introduced by D. F goes here and F goes here, and D comes out of the queue. So next, explore neighbors of E. So current becomes E. And from E we cannot visit G because this is 0. From E we cannot visit D because although this capacity is greater than 0, D is already visited. And we cannot go to B because B is already visited. So we cannot do much with E. So let's move on to F. So with F, you cannot go back to D although the residual capacity is greater than 0 because D is already visited. So the other one is G. And with G we found the sink. So let's say that G got discovered by B. So now that we have found sink, let's regenerate the path back to A. So G got introduced by F. And F got introduced by D. And D got introduced by C. And C got introduced by B. And B got introduced by A. Let's look at the capacity, residual capacity on each of them. So A to B is 3. B to C is 4. C to D is 1. D to F is 4. And F to G is 7. So the minimum on this path is 1. So that's the maximum flow allowed in this path. So this is 1. So we add 1 more to the current maximum flow we have found till now. Also, we're going to go back and reduce the flow on each of this on this path. So FG now becomes 7 minus 1, 6. And this becomes 3, 2 plus 1, 3. In the opposite direction it becomes 3. Then DF, so this now becomes 3. And 1 in opposite direction becomes also 3, 2 plus 1, 3. Then we go to CD. So CD, so this becomes 0. And 1 in the opposite direction becomes 1. Then we go to BC. So BC, so this becomes 3. And 1 in the opposite direction becomes 0 plus 1, 1. And finally AB, so this becomes 2. And this becomes 1. Alright, so this is how we have updated our residual graph. There is one more augmented path. Let's find that quickly. Again, repeating the process. A goes into the queue and A goes into visited. So let's look for the neighbors of A which are not visited and have residual capacity. So we just have B. So we add B to visited. Say that B got introduced by A and add B to Q. Now we are going to pop B out of the queue. So current becomes B. And we are going to look for neighbors of B where residual capacity is greater than 0 and is not visited. So that's C and A is already visited. There is a residual capacity here, but A is already visited. There is no here, so only C. So C got introduced by B. C is visited now and C goes into the queue. So let's repeat the process for C. So C comes out of the queue. Let's look for the neighbors of C. So there is 3 here, but A is already visited. There is 1 here, but B is already visited. There is 2 here and then there is 0 here, so only E. So let's add E to visited. E goes to C and E goes into the queue. Now let's look for neighbors of E where residual capacity is greater than 0. So C, there is 0, this is 0, this is 1 but B is already visited. And then there is D where residual capacity is 1. So we add D to the queue and say that D got introduced by E and also add D to the visited set. So next let's explore neighbors of D. So let's take D out of the queue and explore neighbors of D. So this is there but A is 0. A is already visited. C is there but C is already visited. E is there but E is already visited. But F is not visited. So F got introduced by D. Let's add F here and F here. So now let's take F out, and F has D but D is already visited, so it goes back to G. So at this point of time we found our sink and G got introduced again by F. So let's retrace our step back from G to source A. So G got introduced by F. Let's see who introduced F. D introduced F. and D got introduced by E, and E got introduced by C, and C got introduced by B, and B got introduced by A. So this is our BFS path from source to sink. So A to B is 2, B to C is 3, C to E is 2, E to D is 1, D to F is 3, and this is 6. So the minimum here is, minimum residual capacity is 1, so we can get maximum 1 flow, which we add to the maximum flow we found till now. So now we go back and update the flows here. So 6 minus this 1 flow will become 5, and the opposite direction, now this becomes 4. Then we go to D to F, so this now becomes 4, and this now becomes 2. Then we go to E to D, so E to D, so this was the flow which got us, so this now becomes 0, and this increments by 1 to 2. Then C to E, so this now becomes 1, and this becomes 1 as well. So again, going from B to C, so in the direction from B to C we reduce the flow by 1, so this becomes 2, and in the opposite direction we increase the flow by 1, so this becomes 2 as well. And finally from A to B, so we decrease the flow in this direction, so this becomes 1, and we increase the flow in the opposite direction, so this becomes 2. So after we are done doing this, let's try to find another augmented path, and we should not be able to find any other path. So we can go to B, from B we can reach C, from C we can reach E, but E has no more way to reach G. So ultimately, after this, if you repeat the BFS process, you will not find an augmented path from A to G. So at this point of time, the program can terminate, and this here is our maximum flow which we have found till now, which is 5. So this is our Edmonds Karp algorithm and Ford-Fulkerson method. So again, repeating the entire process, you have to do a BFS. To do the BFS, you find augmented path. To look for an augmented path, you look for the neighbors which are not visited and have a positive residual graph, positive residual capacity. And after you do the BFS, you retrace the path back using this map, and in that all the edges, you look for the edge which has minimum value, and then you subtract that value from all the edges in that direction and add the value for all the edges in the opposite direction. And then you keep repeating the process till you keep finding augmented path, and you stop at the point you can't find augmented path anymore. So this is the entire algorithm. So next, let's look at the time complexity for both Ford-Fulkerson by itself and Ford-Fulkerson with Edmonds Karp algorithm. Let's look at this example to understand Ford-Fulkerson method. This example is given in CLRS book. So let's say we were not doing breadth first search, but we were doing depth first search to find augmented path. So starting from S, we go to 1, and from 1 we go to 2, and from 2 we reach T. So this is our depth first. So here the capacity is 100, 1 and 100. So the minimum here is 1. So what happened was we reduced the capacity by 1 in every edge. So this becomes 1. So this side we increment by 1, and this decrements by 1, and then this decrements by 1, so this becomes 99. So after this we again do the depth first search again. So this time we start from S and we go to 2. From 2 now we go to 1 because there is a residual capacity greater than 0. And then from 1 we again reach T. So this time here it is 100, here it is 1, and here it is 100. So again this minimum here is 1, so this becomes 99. This now becomes 0 and the opposite direction becomes 1, and this becomes 99. And now let's say we repeat the process, and let's say we went from S to 1, 1 to 2, and 1 to 2, 1 to 2, and 2 to 3. So this time this will become 98, this will become 98, and this will flip in the opposite direction. So as you can see, the worst time complexity for this will be O of E into maximum flow in this graph, maximum flow in this network. So if the maximum flow is very high number, let's say this maximum flow was million, this algorithm does not give a very good time complexity. So let's look at the time complexity for Ford Fulkerson with Edmonds Karp. In Edmonds Karp algorithm, we do a breadth first search. The property of a breadth first search is that the number of edges from source to sink in a given augmented path will be same or greater than the number of edges from source to sink in the previous augmented path. Also, we know that the total number of edges from source to sink in the worst case will be the total number of vertices. So a path can be going from source and every other vertex to the sink. Now, from the algorithm we discussed before, we know that we found an augmented path and then we did a BFS. The time complexity to do BFS is O of E. So the total time complexity is O of E into total number of augmented paths we have. So the question boils down to how many augmented paths we have. And let's try to understand with this example here. So let's say we have two nodes, 1, 2, with the residual capacity of 1 from 1 to 2 and 0 from 2 to 1. Let's say we found a path, we found an augmented path going from S to T via this edge 1, 2. So let's say that was this path, S to 1, 1 to 2 and 2 to T. Here the minimum capacity, residual capacity is 1. So this edge here, 1, 2 is called critical edge. Every augmented path is going to have at least one critical edge. So now the question is how many times an edge can become critical edge. So after this path is done, after this flow is done, we would decrement this residual capacity by 1, so this would become 0, and we would increment the residual capacity in opposite direction, so this would become 1. So now for this path, for this edge 1, 2 to be critical again, we want this value back to be 1 and this value to 0. So for that to happen, we'll need to have a flow in the opposite direction from 2 to 1. So let's say this was this flow. Because of the BFS property, there will be at least one node between S and 2. So now we found this path here. So after this path is done, this edge will become 0 and this edge will become, this residual capacity will become 1. So now we found another path going from 1 to 2, and let's say this was this path. Again, because of the breadth first search property, the last time there was just one edge. There was one edge, one edge away from S. This time it's going to be at least 3 edges away from S. One is going to be 3 edges away from S. And then we find this 1, 2 and T. So again it reverts, this makes it 1 and this makes it 0. So after this, when we find, again, when the next time 1, 2 becomes critical, it will be at least be 5 edges away from S. So now we know that in the worst case, the path will have V edges. So basically, an edge can become critical only V by 2 times. And if every edge becomes critical V by 2 times, the total number of critical edges we can have is V by 2 into E. And every augmented path has at least one edge, one critical edge, which means that we can, in the worst case, we can have V into E augmented path. And for every augmented path, it takes O of E time to do the BFS. So there is another E. So the total time complexity for this algorithm will be O of V E squared. Hopefully that helps you give some insights on how this is calculated. There is a clear proof in CLRS book and you can also check it out. So next, let's look at the code for this algorithm.
The main function here is max flow. It takes in the capacity matrix, the source and the sink. Capacity matrix stores the capacity from one vertex to another vertex. For example, capacity 0, 1 stores the capacity of the edge going from 0 to 1. Residual capacity initially is going to be same as total capacity because there is no flow in this network. So we initialize residual capacity to be same as capacity. This parent map is going to be useful to retrace the steps back on the breadth first search. Augmented paths is a list which is going to be used to store all the augmented paths we found so far in this network. Max flow initially is 0. So we go into this while loop till we can find an augmented path from source to sink. So this BFS takes in this residual capacity, the parent, which will be populating the path for the BFS, the source and the sink. So once we find one such path, we go into this while loop and we initialize our augmented path. Our flow initially is a really big number. We retrace our steps back from sink to source using this parent, and we find which one has the minimum residual capacity, and that residual capacity will become the flow of this particular path. Remember before from the video, the flow is the minimum of all the edges for that particular path. And then we also add all the vertices to augmented path, and then we're going to add this augmented path to augmented paths. And then the max flow will become max flow plus the flow we found in this particular augmented path. We are again going to retrace our step back from sink to source, and this time we are going to decrement the residual capacity from U to V by that flow and increment the residual capacity in the opposite direction from V to U by that much flow. And we keep repeating this process, so we keep staying this while loop till we can find augmented path from source to sink for this particular residual capacity. And once we are done with this while loop, we return the max flow we found in this network. Let's look at this method BFS. So BFS is our regular breadth first search. It takes in the residual capacity, the parent map, and source and sink. We initialize visited set, we initialize a queue, we add source to queue and visited set, and then this found augmented path initially is false, and if we do find an augmented path, we are going to set this to be true. So while queue is not empty, we pull from the top of the queue. For every vertex, we check if the vertex is not in visited and the residual capacity UV is greater than 0. So it means that there is some capacity left from U to V. Then we add V to the visited, we add V to the queue, and we update the parent saying that V got introduced by U. If this V becomes equal to sink, it means that we found a path from source to sink, so we set found augmented path to be true. So in the end, either this while loop will terminate because queue becomes empty, or we break out of this while loop because we found an augmented path. In either way, we return the fact that we found an augmented path or we did not find an augmented path. And based on this while loop will break out of this while loop. So this is the code for Fulkerson and Edmonds Karp algorithm. Let's quickly run this code. So this prints all the augmented path and it also shows the maximum capacity. So this is all I have to talk about for Fulkerson Edmonds Karp algorithm. I also have a code for Python, and the link to both the code is in the description section of the video. Please like this video, share this video, comment on this video, check out my Facebook page, and check out my GitHub link. Thanks again for watching this video.